here about this. This is a very simple example to help you understand the difference between a population distribution and a sampling distribution. If you ever forget, just think about the words. What is a population? Let's bounce back to last semester. What's a population?
Everyone.
It's everyone. Yeah, it's everybody. So if I say to do a dot plot of the population, what am I asking you to do?
Plot everything, everyone.
Plot every data point. So if I do a population distribution here, and it was 60, 70, 80, 90, what does one dot represent on a population distribution? What does that dot represent? One score. One individual, and the context one individual with a score of 90. There's a very important distinction that we're going to make here. Because when I bounce down here, then I'm saying, okay, take a sample of any two scores. I happen to pick 60 and 70. So my X bar is 65. Here's notation right here. You ready? X bar is a sample mean. It is a mean of one of the samples, in this case of size 2. So then what I ask you to do is to find every sample of 2. So we came up with 6 samples of 2, so in no particular order. So each of these samples has a sample mean. Each of the samples has an X bar. Are they all the same? Obviously not, right? Because an X bar is different for each of the 6. What I'm asking you to do now is make a dot plot using the means you found in number 3. Is this a population mean or a population distribution?
No.
No. Why not? In fact, how many of these data points that I'm going to plot, how many of them are actual values that were recorded above? Just 2 of them. So the other ones aren't even represented by things from the population because this is not a population distribution. What we're making is called a sampling distribution. So let's make it.
Just number 4 isn't a population distribution?
So what I'm helping you to do right now is to draw a distinction between a population distribution and a sampling distribution. What we made up here was a population distribution. One dot represented one with an individual score. Well, in the population distribution, we plot all the dots. So in this case, it was 4. What if we had 50 people take the test? How many dots would we have?
50.
We'd have 50 dots. Down here, in the sampling distribution, we are plotting the means of certain samples. It's every sample, but they're means. And so, how many dots are we going to have on this one down here?
6.
6. But how many scores did we have?
4.
You see the difference here. So the population distribution is going to have a certain number of dots based on how many scores. The sampling distribution is going to have dots based on the number of samples of size n, in this case 2. Gigi.
So, okay, like that's really confusing what you just said.
Yes, it
Just
is.
to make sure that like, so the population distribution, number 1 is like 1 dot represents 1 score, and then number 4 is just 1 dot represents 2 scores.
Yes!
Mean?
Yes, that's exactly right. That's why we labeled this dot. And you're kind of like, it's 1 score of 90, what's the big deal? It's not a big deal until we start doing something different with the numbers that people are like, wait a minute, hold on. A dot is not just a dot, it's not just 1. No, it is 1. It's 1 mean of a sample. All right. 85. So my plot looks like this, 65, 70, 75 twice, 80 and 85. Let's break this down. This dot represents 1, and we've got to have context here, sample of 2 with a mean of 85. Let's label this. This is a sampling distribution. Notice what I put here, a sampling distribution of X bar. So in number 5, not to further confuse, but to hopefully clarify. In number 5, what am I asking for? And Madison, what does that mean? Like, how do I find the mean of a group of numbers?
Average.
That's right. So the mean of my population would be 60 plus 70 plus 80 plus 90 divided by 4, which gives me 75. Here's how we're going to label that. You ready? Because it's the mean of the entire population, this is called the population mean.
Wait. So in this case, it's a population number.
Is it supposed to be M or a U or something?
It's the name is escaping me right now.
I know it's a mu, but
Yes, it's a mu. Yes, it is.
It's a mu.
It's a U. Yeah, it's a little U. On your calculator, it's going to look like this. Your calculator is going to look like this. Okay. So what are we talking about here? Because I just threw basically 4 things at you. The first one was an X bar. An X bar is a sample mean. Well, what's a sample mean? It's the mean of some sample. So what if I said take a sample size of 3 and find the mean? You'd add up 3 of the numbers and divide by 3. And then you'd have an X bar of that particular sample, right? So how many X bars are there for a given data set?
Unlimited.
What does it depend on?
The amount of people, like originally, the amount of like scores you have.
Size.
Oh, the difference, the like variability, or like, oh no, the unique values.
Size.
No.
Well, to be fair, it does depend on the unique values, but the size of what?
I mean, it says size
Population
too.
size.
Size.
Not population. Yeah, it does somewhat
How
depend
many
on.
do you pick?
It depends on how many samples you take. Right? So how many samples you take? So in this case, because I was taking samples of size 2, I had 6 samples. Well, what if I did samples of size 3? How many samples could I take out of the 4?
Wow.
That's the question, right? So the question is, how many samples am I taking? That's your particular X bar. So now, how many population means are there?
1.
There's only one population mean. So your sampling distribution has a bunch of dots because there's a bunch of sample means. When I put my population mean on the dot plot, there's only going to be one population mean. This is how we're going to do it, right here. You ready? Big line. We're going to label it. Mu.
10.
Equals 75. It's on a solid line in this case. We're going to say that equals 75. Yes.
The population mean of the population.
What a fantastic question to ask, Leon. So it's not a problem when I have 4 scores. What about when I have 400 scores? What about 4,000 scores? What about 4 million heights? What about 5 million weights? What about 7 billion ages, if we're like, what's the mean age of people on the planet? That's what we're going to talk about. As we start to look at this chapter 7, what we're going to develop is the necessary conditions to say, okay, how many samples do I have to take before I can say, okay, the population mean is about this, or it matches this. How many samples do I have to take? How many trials do I have to run? That's the question we're going to be answering. Because could we survey everybody in the United States about their age? Yes. Logistically speaking, can we actually survey everyone in the United States about their age? Not really. Okay, the census, vastly imperfect, right? So now as we work through this, that's what we're going to be looking at. So let's talk to the next page of notes at the top. And hopefully when you saw that review of the first semester, you understand the importance of these box notes. So you see the importance of these box notes because these are going to be the place. This is going to be the place where we kind of distill a lot of info here. Parameters. And statistics. Here's why we're dealing with statistics. Statistics are numbers that describe a sample. So a statistic is a number that describes a sample. As opposed to a parameter, what do you think a parameter is going to be? A number that describes what?
Population.
That's right. So a parameter is a number that describes a population. When we look at this, I'm going to use this here. I'm going to make a little chart right here. We're going to talk about three things. So three measurements. We're going to have different symbols for a statistic and a parameter. So the first one is going to be a mean. The second one's going to be a proportion. The third one is going to be standard deviation.
Sounds like straight, like online.
I know it's like evenly spaced. I'm like, yes, we got it. When we talk about the mean in terms of a parameter, we already talked about the symbol. So what was the symbol that we used to describe the mean of a population? Population. What was the one we used to talk about the sample mean? There were a bunch of them. That was X bar. Remember the mean of that sample, all those samples that we took? X bar, X bar, X bar, X bar, X bar. We haven't talked about this yet. We are going to talk about it as we move through here. But sample proportion versus parameter proportion. So population proportion versus sample proportion. This is what we're going to talk about. Like 40% of all Americans say this. Okay, well, 40%. So that's a sample proportion. So we're going to be talking about like a probability there. The sample proportion for a parameter, a proportion for in a parameter sense or for a population is going to be a p. For a statistic, and that's a hat, by the way. I tried to smush it in. For our standard deviation, we've kind of touched on these, but this is going to start becoming, no pun intended, significant. So this is going to become significant now because we are going to look at what's the distinction between a sample and a population. And so our standard deviation and our, for a parameter and statistic have two different symbols. All right, now,
What's the prop?
proportion. Proportion. What I'd like for you to do is work through this, check your understanding. You are going to be able to kind of identify some things, and this is a useful skill to be able to discern, well, what are they talking about? What's a sample in this case? Parameters and statistics. We are talking about proportions here. So when you get to that part that says the parameter, you're going to be looking at a proportion, so you're going to have some fractions there. That's my note for you on that. I want to give you about 5 minutes to work through this, and then we're going to come back together. Hold on one second. Walk through this. So the first question, and I could see it, and I was hoping this would come up. The first question that popped into your mind, but you didn't actually ask it because I don't know that you knew this was the question that you had, was what are we actually looking for in this problem? What we're going to start to do in these problems, we're going to start creating the likelihood that something happens. And then we're going to measure it. What are we trying to look at the likelihood of happening here?
Red chip.
Red chips out of what?
Bag.
Out of a bag. Yes, red chips out of a bag. And then the next piece is, well, how many red chips were there? Okay, there were 100. Well, out of how many? Oh, because 100 out of 10,000 is much different than 1 out of 200. Is much different than 1 out of 101. So the first question you need to ask is, well, what are we looking for in this problem? We're looking for the proportion of red chips. And so when I think about that, then I'm thinking to myself, okay, now everything I'm measuring with parameters and statistics should be related to the proportion of red chips. You can even write that in the margin, proportion of red chips. Everything you're looking for in this problem is related to the proportion of red chips. Guess what? We're going to do this with M&Ms. We're going to do it with Reese's Pieces. We're going to do it with, whatever. But the question is always, what am I looking for? Number of red chips is not enough. Because number only tells me a quantity. 100 out of 200 is a lot. 100 out of 10 million is not a lot. So you got a proportion of red chips. So what's my population? Meaning, what's everything that I'm looking at here?
200 chips.
It's 200 chips. My sample that I pulled is what? 20 chips. Here's something very important. Are you ready? Don't forget this. Randomly chosen. We are still obsessed with random. It has to be random. So you should say 20 chips randomly chosen. So then, in your mind, you see parameter and statistic. You should immediately be thinking, boom, number. This answer is going to be a number. So when I ask you about parameter, and people are like, well, I don't know. In the last one, it was mean. Are we finding mean in this problem? No. Then you have to go back to, what am I looking for? So if it's proportion of red chips, proportion of red chips, what is the parameter, meaning the population proportion of red chips?
100 out of 200.
There's a couple of things you have to do here. 100 out of 200 equal to 0.5, sorry, watch this. You should label it thusly. P equals 100 out of 200. Why don't we reduce it?
Because it's true.
You can still see the total, and you can still see the population.
Wait, does it need the hat over the P?
What a great question. Where should the hat go?
Statistics.
Down below.
Huh?
So in the second line, P hat is a symbol that represents a sample proportion. So in our sample, P hat is what? 7 out of 20, which was 0.35. When you go to number 2, this is going to be so basic. But they're asking you, what is evidence that less than half of the chips in the bag are red?
Statistic doesn't match the
That's right. Well, so maybe you don't know the parameter. Because maybe you don't know. So what if I took a bag of M&Ms and I just divided it into samples of 20? I just divided, and I didn't tell you what the overall was. Anika gets a handful of 20, whatever. There's only 7 red ones. So what's Anika's evidence that less than half of the bag is red?
She has 7. You have 10 out of
I have a strong hunch it's probably likely. No, your evidence is sitting in your hand saying, there are not 10 red chips in my hand. That's my evidence. So what's our evidence that there is no alien life? I've never seen one. Is that compelling evidence?
No.
Maybe not. But the fact of the matter is, what's the evidence here? The evidence is,
Jenna pulled 7 out of 20, and that's less
The-
than half.
yes, the sample on fire.
Yes.
The sample had only 7 of 20 chips that were red.
Maybe I should get notification that said that. Maybe these rats would make me a zombie.
So this part admittedly is going to get confusing. This part is going to get confusing, so I want you to stick with me here. They say, what are, so 2 explanations for that evidence. So let's say Anika's sitting there. And she pulls that there's 7 out of 20 in her hand. Okay? How might that have happened?
She just less than half of red.
Yeah, that's one of the reasons. So one of the reasons is there might, there are less than 50% red chips in the bag. Hey, stay with me because this could be confusing. So it could be that she pulled out a very representative sample and there are really less than 50% in the bag. Or what else might have happened?
She didn't choose enough red.
It's her
No,
fault.
unlucky. It's unlucky.
They could be all red except for the 13 that she picked. That worked.
She could have eaten some.
We got 7 out of 20 purely by chance. Those are the only 2 explanations. The temptation for you is going to be like, well, there was a hole in the bag, so some of the red chips fell. Don't go there. Don't go there. I say that because the temptation when we write about these things on an AP test would be to try to explain like what possibly could have happened. Don't make things up. It's one of 2 things. Either the sample's representative or it happened by chance. Those are the 2 reasons to explain evidence and statistics. Either it is that or by chance that happened. And what we're going to end up evaluating is how likely was it based on the actual data that she got 7 out of 20 purely by chance. Because what might have happened is 50% of the people that pulled out of the bag got 7 out of 20. Well, does that mean that the true mean was 50%? Who knows? That's what we're going to evaluate. Okay, so then we use technology to simulate choosing 500 simple random samples of size n equals 20 from a population of the 200 chips, 100 red and 100 blue. The dot plot shows p hat, the sample proportion of red chips in each of the 500 samples. So what happened here? Talk me through the experiment.
They did it.
They actually did it, and what was one of their baseline assumptions? The most basic assumption when they did the simulation was what?
There's 100 red and 100.
Which means what?
It's 50%.
They set it to make the claim true. They said, okay, let's just assume that it is 50%. I'm going to run this simulation, and the simulation is going to spit out on the other side how many times a certain sample size with a certain proportion of red came up. Does that make sense? This is one of those things, I'm telling you right now. You're going to be like, oh, that makes perfect sense. And then you're going to think about it in 5 minutes. You're going to be like, wait a minute, hold on, I'm confused. What happened? Whenever we run a simulation, we're going to assume that the claim is true. Now, there's 1 dot on the graph at 0.80. Explain what this value represents. Work on that in your group for a second. What does that 1 dot represent?
Let's come back together. So let's think about this. So the stated fact is 50% are red versus blue. So that was the assumption we made when we did this. So if the assumption is that they're 50% red, 50% blue, they ran this simulation, and what they found was this thing that looks like a bell curve. We're going to talk about why it looks like that and why that's awesome for us moving forward. But when we look at this one particular dot, this one dot on 0.8 here, what does the one dot represent? You all have it right. I checked your papers. Be bold. One sample with 80% red chips. One sample with 80% red chips. But Mr. Saris, the assumption that they made was that 50% in the bag were red. Yeah, that's great. But what they did was they simulated someone actually pulling them out and calculated for us, and they put them all together. There are 500 samples here. This is very dense. Okay, it's very dense. So now, would it be surprising to get a sample proportion of p hat is equal to 7/20 or 35% or smaller in an SRS size 20 when p equals 0.5? So they put this qualifier on here because you could do this a bunch of different ways. You could do samples of size 30. You could have made a different assumption that 60% were red. But what they're saying is, for these assumptions, was it weird to get 35% or less? Well, I like to draw a little line here, and I look at this. So what they're saying is it strange to have a dot that falls where those dots fall? They're not asking you necessarily to do a statistical breakdown in this question. They will in the next one. But what they're saying is, no, it's not weird. A sample with 35% or less red chips happened often. The example that I gave to the group over here was, you're asking the question, was it weird that this happened? So I like to ask an even more extreme question. Is it weird to get 10% red chips? How do you know? Because when you look, are there any on 10% or less? Is it weird to get 15% or less?
Yes.
How many were there? Just one. So that would be a little odd. What about 20% or less? I see. Hold on. Okay, hold on. I got it. All right. So the graph is misleading in this case. They've packed in the dots. They're very small. I went to the original graphic prior to copying, and I forgot. I forgot to. I meant to show I meant to drop the picture in here so you could see. When we're looking at these samples, what we're evaluating is two things. The first one is, no, a sample happened. It's on the graph. There are instances where this happened. What we're going to be doing is evaluating this 5% level. Now, given the number of samples, how close did we get to 5%? Hold on to that for just a second. What we're going to look at here is we are going to not necessarily use the statistical significance in here. The graph is misleading. But what we can say is this. This is the most confusing part of Chapter 7. Are you ready for it? Mm-hmm. Okay? It's the most confusing part, but I'm going to explain it to you. I'm going to let it soak in, and then we're going to explain it again. What claim is true because Anika's sample of 7 out of 20 being red was okay to have? Like, it was okay that she did this when we did the sample. So what claim is true now?
That it's smaller. There's 50%.
That's right.
Well, there's 50% red chips in the bag.
How do you know it's true?
Haha, see, that
was okay.
this is why, okay?
It's not statistically significant.
Right. Okay. So here's what we can say. So what we can't say is what we can't say is there are 50% red chips in the bag. We can't say that. But what we can say is there's not enough evidence not to say or there's not enough evidence to say there's less than 50% in the bag. So think about Anika's sample for a minute. Okay? So she's got this 7 out of 20 sample, and she's like, there's not 50% in this bag. I only have 7 of them. So then she's like, I'm going to do an investigation. So she puts together this very elaborate graph, and she finds out that, oh, it wasn't weird that I got 7 out of 30. Even though there could be 50% in the bag, 7 out of 20 wasn't that weird. So what can we say? What we can say is there is a large enough chance. There's a large enough, so this is number 6. And we're going to talk about the 5, I'm going to talk about the dots here in just a minute, okay? So get ready for the dots. There is a large enough chance that we get a proportion a sample proportion so there's a large enough chance that we get 0.35 as a sample proportion purely by chance that there's not convincing evidence that less than 50% are red in the bag. So notice what I didn't say. I didn't say, oh, there are for sure 50%. What I said was, there's not convincing evidence, and what we're going to say eventually is, to reject the claim that there's 50% in the bag. But for right now, what we're saying is, no, we cannot, there's not convincing evidence that less than 50% in the bag. Because what's Anika sitting at, and think about it, she's sitting over there thinking to herself, there's got to be less than 50% in the bag. I only got 7. And so she runs this test to see if this was weird, if this sample was weird. And what we just determined by looking at our graph and seeing that it happened in a large enough chance, well, what's large enough? Well, so the dots here, it's actually not to scale. Okay, it's not to scale. The intention of the book was not to put it to scale. They put little wobbly dots, and I can show you if you have your book, you can see. They actually make the columns like this. Why? Because they're simulating that there's actually dots there. We're going to talk about, in the next lesson, we're going to talk specifically about counting the dots. But the intention of this lesson is to say, there's enough dots there, there's enough dots there to say that this wasn't an accident. This could possibly happen, and so we can't say that the claim isn't true. Are you okay with that? All right, let's go on to the next one. So for the next one, actually, hold on a second. Okay, the next one, you're going to need your calculator here because you're going to have to simulate your score on the Chapter 6 test.
This says day 2. No, I don't know if we should rush it.
Wait, can you, so the lowest one is 70 what?
Lowest one is 78.
Minus 1, and then what's the other one?
Oh, the one's what?
79.
79 is 0, 80 is 0, 81 has 3. So answer this question. What does each dot represent?
No. Meter. X bar.
So bad at this.
One sample of 5 test scores. And the sample mean, or X bar. So this right here, this little dotty dot, that's an X bar. Here's an X bar, here's an X bar, and you get an X bar, and you get an X bar. All of these are X bars. So what do you think the true mean is? That's a guess. You can guess that. That's a great guess. When we talk about true chapter 6 average or true mean, what we're talking about is mu. This is what we're talking about. So maybe you guessed 89. That's not bad.
83 was 1.
83. 81, 82, 83. 83 has 6.
I'm just gonna.
82 has what? 1?
95.
So a sampling distribution shows the means calculated from all the possibilities. All the possibilities.
No.
So, do we have a sampling distribution?
No.
No. How many possible samples of size 5 would there be?
$65.
How'd you get that?
5 times 30. More. Oh my god. No. 52.
Blast from the past. Are you ready?
Why is
So how many people do we have here? 2, 4, 6, 8, 10, 12, 13. We'd have to take 13 combined 5 at a time. That's the total number. What is that number? 1,287? This is why we use technology to simulate these. It's a lot, right? Okay, it's a lot.
Oh, wait. All samples.
How do you do that in your calculator?
What is 13?
So you have to do NCR. It's a math problem.
Wait, so what are we doing?
I don't know why.
I don't know.
So you have to go back. You put 13 in there. Now scroll over and put 5 in here.
Wait. So, Josie. Wait, with this? 13. Okay.
So ours is not a sampling distribution. Now, we could have done a sampling distribution, but it would have been exhausting to figure that out. I mean, this is months of work, right? But a true sampling distribution takes into account all of the possible samples of that size. Now, at the bottom, we took a random sample of 5 midterm scores at Rockford High School and got a mean of 68. Is this convincing evidence that Rockford students did worse than students at our school?
Well, can
Where did you get 13 and 5 from?
you explain
We have
what-
13 people in this class,
Yes, because our.
and we took them 5 at a time.
Oh.
Yeah, well,
we didn't
that
have
doesn't work because we set a limit on ours. Like ours was 65,
It's true.
Oh.
so you
It's
can't
true.
compare it.
So,
Oh,
I mean, that wasn't really the limit. Just assume that we all did well in study.
yeah, but
in the past.
why don't the rock? Yeah, what if the Rockford?
we didn't open ours up all the way. Okay, so let's talk in theory. We had to do this because I had to simulate it. What would be convincing evidence?
If less than.
Like, what would we look for convincing evidence?
Then
So
how-
let's say we had another section of AP Stats. All right, and their test scored, and they had an average of 79. Is there convincing evidence?
No.
They did worse.
It depends on the sample size and
Yes, ours doesn't even have it.
Yeah.
That's the other.
So there was only a 2.5% chance. Because remember, in their class, we would have only taken a sample of 5. So let's say the sample of 5 that I got from their class was right here. So what I would be evaluating is this, right? What is the likelihood of getting 79 or less purely by chance?
But all of those are our class, and then there's 1 point from their class.
I know, but what we're evaluating is the likelihood that their class average would be by chance, like ours. So ours by chance. So we're evaluating it versus, right? So there's only 2.5% chance that ours was that low. That's not very likely. So it's likely that ours is higher. Okay, that's the concept that we're working behind.
So yes.
Yes. Yes. Okay. So what we have in our sampling distribution, this is beautiful, is called an unbiased estimator. Okay. So we're always evaluating the likelihood of it happening by chance versus what actually happened in our sample.
Which indicate
So we would love to have an unbiased estimator. So what we have in ours is an unbiased estimator. If you hear me say that, that's a good thing. Because unbiased estimators would be for Madison to say, I think the class average was 89. And then we do all the things and we determine that it is 89. And then Madison's like, wow, I'm a great estimator. It's unbiased, right? It's the same. So an unbiased estimator is when a statistic is unbiased
What are you possibly laughing about?
Shut up.
Because the definition of an unbiased estimate is a statistic that is unbiased.
A statistic is unbiased if the mean of the sampling distribution
Sounds like an insult.
Unbiased estimator.
What's sad is like by the end of this chapter, I know what's going
if the means match. If mu matches x bar, then it's unbiased.
What's the last
The wrong parameter.
one? Unbiased. If the mean of the sampling.
Is that true always?
Yes.
So basically, if you make a correct guess, you're unbiased.
It matches the mean of the parameter? Or just the parameter?
And so here's what we need to talk about. Like, how does it happen that they match? We just make a good guess? No. We make educated guesses based on a certain number of samples. And then we make some estimations based on sample sizes, and we're going to talk about that next time. But that's the basic gist of what's going on. Okay, now, here's what I'd like for you to do. You might struggle a little bit with the last little part of this, but basically, your homework is going to be outlining like identifying parameters and statistics, evaluating some things. Here you go. 1, 3, 5, 7, 9, 11, 13.
Step 9.
I know, discrimination.
Grace, did you find a photo?
Wait, where are those numbers coming from?
So, this is from section 7.1.
Oh, that's our homework.
That's your homework.
Runway?
Yes, it's on RenWeb. I will put it on Edmodo as well.